Alright, today we're going to get into what's called aqueous equilibria and chapter 15. And we're still on the whole K version. You know, you've still got the Kas that are going to be big, the Kbs that are going to be big, and we're going to also introduce this one called KSP, which is going to deal with solubility. So a lot of it's putting a lot of things together, so you're going to have to spend some time and wrestle with it in order to understand it. Alright, the first thing we got to talk about is what's called a common ion effect. And this is a shift in the equilibrium position that happens when an ion already involved in the equilibrium is added to the solution. It's a application, really, of Le Chatelier's principle. And it's very important with polyprotic acids. So for example, what effect does the presence of dissolved sodium fluoride have on the dissociation equilibrium of hydrofluoric acid? Okay, so what does the chemistry look like? Now, for some of these, you guys are going to have to write down some of the work. I think this is another one where you have most of it, but not all of it, so you just want to pay attention to your notes and make sure you have everything written down. All right, we have a solution of hydrofluoric acid, which is a weak acid, Ka of 7.2 times 10 to the negative fourth, and sodium fluoride. Now, sodium fluoride is going to donate the fluoride ion. So when we talk about the whole common ion thing, we're talking about the fact that we have the fluoride ion in both solutions. So these are all of our major species here. Again, the common ion is from the sodium fluoride and the hydrofluoric. Why do we want to consider breaking apart the sodium fluoride first as opposed to the hydrofluoric? Well, hydrofluoric is a weak acid. It's essentially a weak electrolyte. So it may force the dissociation constant back to the left because sodium fluoride is soluble, which means it will completely dissociate into the sodium and the fluoride ion. And so what it's going to do is it's going to force the hydrogen ion to be lower than would be predicted, and the pH will be higher than expected. Okay, so just as a reminder, this is the chemistry back up here. If we add fluoride ion, just because of the Chatelier's, it's going to force it to go backwards. And that's why it's going to raise the pH, which is going to make it a little bit more of a basic solution. Okay, so you can see there's a lot of application in this chapter where we kind of pull things together. Okay, so example number 2, how would the predicted pH and the actual pH compare for aluminum chloride and ammonia? So if we have ammonium chloride, we're going to dissociate into ammonium and the chloride ion. And then remember the chemistry, the acid-base chemistry for ammonia is ammonia plus water is going to give us ammonium and hydroxide. So if we add more ammonium into the solution, it's going to force this reaction back to the left, and it's going to lower the amount of hydroxide, which is going to increase the hydrogen ion, which is going to lower the pH or make it more acidic. Okay, so really you have in this unit, we start to manipulate these variables to figure out where we can put solutions so that we want them. All right, let's look at example 15.1. The hydrogen ion concentration is 2.7 times 10 to the negative second at equilibrium, and percent dissociation is 2.7 for a solution of 1.0 hydrofluoric. We want to find the hydrogen ion and percent dissociation, in a solution of 1.0 molar hydrofluoric and 1.0 molar sodium fluoride. So here we've got an application to our common ion effect. It gave you the Ka value, 7.2 times 10 to the negative fourth. Our major species still, the Ka is greater than Kw, so water is there, but it's not going to influence the pH very much. So we've got the hydrofluoric dissociation right here, and our common ion is going to be the fluoride ion. So it's going to drive it back to the left. Because of that, we just got to figure out how much it's going to drive it back. So here is our ICE table. Again, you want to check. I know you guys need to write down some of this work. You have hydrofluoric. And remember, the only other thing we're adding in, it's kind of like the polyprotic idea. We have to add in this 1.0 at the beginning of the ICE table, simply because of the sodium fluoride. Okay, because that fluoride ion is going to split off and already be in solution. So we solve for X. Our assumption is going to work here. It's going to come out to be less than 5%. Okay, so I'm showing you a little bit of work here. This is all going to cancel out, so X is going to be equal to the Ka value, which is 7.2 times 10 to the negative fourth. and it's going to give us a pH of 3.14. Now, if we find the percent dissociation, it drops that percent dissociation all the way down to only 0.072%. So this is really just to illustrate the fact that the common ion effect really can significantly influence how much acid will dissociate and what the math will look like. So that's why it's important. Okay, now we're going to talk about buffers. Buffers are kind of it puts a lot of things together. So you got to spend some time. You may need to go back to the textbook. You may need to reference Shakashiri, but you got to go back and wrestle with this buffer stuff. And I'll see if I can find some other videos that explain it well. But a buffered solution is a solution that resists pH. Okay, remember, even if you think about a buffer in general, a buffer is something that helps two parties get along or that resists change. And so now we're just talking about chemistry that resists change. And here are the combinations. It's either made from a weak acid and its salt or a weak base and its salt. Okay, and I'll show you kind of what that means, where those combinations come from. But ultimately, you need two parts because you need something that can absorb the change in hydrogen and something that can absorb the change in hydroxide. And I'll show you the chemistry of what that looks like. Okay, so if we look at 15.2, you have a buffered solution contains 0.5 molar acetic acid and sodium acetate, and we have to find the pH of the solution. Okay, and we do buffers now because this really is essentially, buffers are also a common ion problem because we're going to have acetate dumped into that solution, which is going to influence how much the acetic acid is going to dissociate. Okay, so again, we've got our acetic acid, our sodium, which really is not going to have much of an influence on anything. One, because it's always soluble. Two, because since it comes from such a strong base, it's so weak that it doesn't have any influence on pH. So our main focus here is going to be the acetic acid and the acetate ion. So we got to set up an ice chart, and again, you have to put into the fact it's a 0.5 molar. So we've got our 0.5 molar of acetic acid, but we also have to add in the 0.5 here simply from the sodium acetate. Okay, that's where this initial 0.5 is coming from. And it's going to change. Again, we're figuring out how much the addition of this 0.5 is going to force the dissociation back to the left. All right, so we solve. Again, everything kind of cancels out. We end up with a pH of 4.74. And we want to kind of remember that number because we're going to come back and compare to it later. But 4.74 is our initial pH value for our buffered solution. Now what we're going to do is see what would happen to the pH if we went ahead and added some solid sodium hydroxide. Okay, sodium hydroxide is a pretty strong base. We're going to go ahead and add a small amount, 0.010 moles, and see what happens to the pH. Remember, what we're comparing it to is 4.74 to start with. All right, so again, our major species, we've got the acetic acid, the sodium's there, but yeah, okay, now we're going to add in hydroxide. All right, so let's see if we can figure out all of these reactions. Okay, when you dump in the hydroxide, remember, this is what we're having. We already know we have a buffer. The new thing that we're adding is hydroxide. This is what's getting added in. The chemistry that's going to take place as soon as you dump that sodium hydroxide into our solution is it's going to, first of all, it's going to completely dissociate. Okay, and then they're going to look for something to react with. Now we know sodium ion is really happy, so it's not going to react with anybody. So that's why I keep crossing it off. But what's going to happen is that hydroxide is going to look for something else to react with in the species. And that's this chemistry right here. Because what the hydroxide can react with is the acid. Okay, and this is a plain old acid-base problem where the hydroxide really, 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 really likes hydrogen ion. So it's going to steal the hydrogen ion and form water. So there goes the hydrogen ion. All right. Okay, there's the chemistry. And then what you're left with is the acetate ion and the water. And then what we got to figure out is essentially how much that acetate is going to drive the, lower the dissociation back. Okay, so how do we do this? Here's our chemistry. Okay, we have, for our moles on these, we had our initial concentration of 0.050. Okay, this is still coming from the original amounts. We knew we had 1 liter, 0.050, which this is just using molarity as a conversion factor, right, because it's moles per liter. So we can get 0.50 moles of our solution. The hydroxide component right here, this is coming from the sodium hydroxide that split off. Okay, that's where the initial hydroxide is coming from. And then remember, we put the water on here. It doesn't influence it because it's a liquid, but we still have the acetate. We're still just using molarity. I'm just fixing the units here. Not fixing, but showing you how they cancel out. Moles per liter to get 0.50 moles. Okay, so when this runs to completion, this is going to be gone. Okay, this is going to be totally gone right here. So this is going to be our change. This is our only change here. So we're figuring out that we know we have 0.010 is going to take away from this and it's going to add to this. And the reason I know it goes to completion is because the whole idea is that it's a strong base. So it's really, we almost are switching this into a equilibrium / stoichiometry chart. Okay, it's a little bit of a reach. We're going to do lots of problems with this in class, but we're almost kind of adding in a little bit of stoichiometry to just understand the chemistry and the changes that are taking place. Okay, but now that we know the amount of acetic acid, now we've got to do our ice table. Okay, so we had to do a stoich table first to figure out what we were going to lose. Now we're going to do our ice table in order to figure out the pH and how much acid dissociated. So these are just the amounts that we got from the stoichiometry chart on the last slide. So we had 0.49, 0, 0.51, because now we got to go back to our regular old Ka problem and figure out how much acid dissociated. So here we've got our, our math and our assumption is going to work. Okay, our 5% rule still works. So this means our pH is going to be 4.76, which means that it only changed by 0.02, because if you remember what we were comparing it to, we had a pH value of 4.74, we added in the sodium hydroxide, and it only went up, which we were expected because we're adding a base, by 0.02, which is not very much. So it means it buffered the solution, it buffered the change, it didn't cause a giant shift. Now, how does it do that? Okay, here's the background. If it's a weak acid and it's salt, it's going to contain large amounts of the weak acid and its conjugate base, or that negative ion, the anion. So when hydroxide is added, the hydrogen, so let's say we added hydroxide like we just did, the acid donates the hydrogen so that the hydroxide does not build up in solution and, cause it to go really basic. On the flip side, if we added something that had hydrogen ion, well, this time the anion is there to accept it, so the hydrogen ion doesn't build up either, okay? Because remember, the big major players in pH are how much hydrogen ion and how much hydroxide. So if there's something there that can accept it and transform it into something safer, then we buffer that solution and we're really happy. If you've ever been in a pool, this is exactly what all those chemicals do, okay? Bodily, people jump in pools and they have stuff on their skin or there's fluid and it dumps in there. The buffers make life happy in that pool because there's something to accept everything that goes in there. Now, as long as the change is small compared to the original concentration, the pH won't change much. Buffers have limits, but we'll talk about that. If it's a weak base and a salt, it will contain large amounts of the weak base and the conjugate base. Okay, so this time, if hydroxide is added, the conjugate base will donate the hydrogen ion so that the OH does not build up to form water. Okay. And when the hydrogen ion is added, the base will accept the hydrogen, so the hydrogen ion doesn't build up either. So for example, if you have ammonia, ammonia can add that hydrogen ion and form ammonium, and you're not ending up with a huge jump in pH. Okay, here's just a visual of what this looks like. Okay, the buffer after the acid is added, the buffer with its conjugate base equal. Here we're adding the acid, here we're adding the base. This is just showing you the chemistry. Remember, we have also treated this as just the hydrogen ion. So if you add the acid in, you're adding hydrogen ion or hydronium, and you're ending up with a weak acid and some more of the anion. If you're adding the base, you get the hydroxide, and you end up with more over this. Okay? We are going to stop here, and I'll start over with the Henderson-Hasselbalch equation in the next video. I hope that helps.